All right, so good morning from Chicago, and well, thanks to the organizers for including our paper in the schedule. This is joint work with Paula Bustos at CEMFI, who's, by the way, also one of the organizers. That, of course, has nothing to do with why this paper is in the program. Joan Monras at the Universidad Pompeu Fabra, and Joan will answer. We will be answering your question in the chat, and Juan Manuel Castro Vincenzi, who's a PhD student at Princeton. So what is this paper about? So the starting point is familiar to all of you, and is the fact that sort of this reallocation of workers from agriculture to manufacturing is sort of fundamental for economic development. And sort of this view is based on two arguments. The first one is that reallocating workers from agriculture to manufacturing can lead to static gains in aggregate productivity if labor productivity is lower in agriculture than in the rest of the economy. The second argument has to do with dynamic gains, in the sense that this reallocation of workers from agriculture to manufacturing can actually lead to dynamic gains in aggregate productivity if manufacturing really is the sector that can generate positive externalities for the rest of the economy. Due, for example, to the fact that innovation happens in manufacturing, that manufacturing can produce inputs that have sort of knowledge spillovers to the rest of the economy. The starting point of our paper is that there is still scarce direct empirical evidence on these dynamic gains, and so we want to bring this is where we think we can make a contribution. And sort of the main message, what this paper wants to emphasize, is that these dynamic gains that I was describing depend not just on the size of the manufacturing sector, meaning how many people actually move to manufacturing from agriculture, but also on its composition, meaning where do these workers actually end up moving within manufacturing, in which industries do they end up moving. So if there is one message that we would like you to sort of take home from this paper, is that which industries within manufacturing absorb agricultural workers can have an impact on productivity growth in the long run. So what do we do in this paper to address this question? So first of all, we use the adoption of genetically engineered soy in Brazil as a natural experiment, and this is something that we've done in previous work. Just to remind you, this technology is a technology that allows farmers to produce the same output with less workers, and in particular, it tends to replace unskilled workers. So you really want to think of it as an agricultural productivity shock that pushes unskilled workers out of agriculture. The second thing we do in the paper is, so we write down an open economy endogenous growth model to think about the impact of this increase in unskilled labor supply on the rest of the economy. I will go through the model, although briefly, and under several assumptions. Sort of the main prediction of the model is that when workers that leave agriculture are mostly unskilled, which seems the case in many instances, structural transformation can reinforce the comparative advantage of the local economy in less innovative industries, and these might end up slow down long-run productivity growth. We sort of bring this prediction to the data, and what we do here, we test empirically, so we trace sort of empirically the effect of this reallocation of unskilled workers from agriculture to manufacturing on three main set of outcomes. First of all, we look at how the composition of the manufacturing sector changes, and what type of sort of industrial specialization this labor flow generates. Number two, we look at what happens to innovation in manufacturing. And for these, we're going to develop a new measure of innovation that is based on the description of occupations of workers as reported in the Social Security data of Brazil. This is a measure that has the advantage of being representative of very detailed level of spatial aggregation, and back to sort of Chris' point yesterday of trying to measure better the stuff that matters to us as economists, when we think this is a potential, we're potentially making some progress here in that dimension. And finally, we're going to look at what happens to productivity growth in manufacturing. Let me give you a sort of a preview of the empirical findings, and I'm going to do that also showing you some key graphs that I'm also going to talk about later. But my experience teaching this quarter is that the attention span in Zoom is quite short. So let me give you sort of the main 4 results right now. So remember what we're trying to do here. We are comparing regions of Brazil that were differently exposed to an agricultural productivity shock that allows farmers to save on unskilled labor. So what we find, number one, is that regions that were more exposed to this shock experience a reallocation of mostly unskilled labor from agriculture to manufacturing, and this is what the figure that you see here shows. This is the impact on the change of low-skilled labor in each sector for a standard deviation difference in productivity shock in agriculture. Second result, we look at what happens within manufacturing, and if you split manufacturing into low and high R&D manufacturing, and this stands for like research and development. Think of this as less innovative or more innovative manufacturing. You see that most of the unskilled labor that moves into manufacturing gets absorbed by low R&D manufacturing. And you want to think of these low R&D manufacturing as footwear, beverage manufacturing, food processing type of industries. Number 3, we look at what happens to innovation within manufacturing, and in particular innovation expenditure. In our model, as well as in the data, you can invest in innovation in both the low R&D industry and the high R&D industry. What we're going to find is that industrial specialization in low R&D industries within manufacturing leads to a relative decline of the innovation expenditure done in the high R&D manufacturing. So there is sort of a reallocation of innovation away from the high R&D industries. And finally, we document that this has potentially effects on productivity in manufacturing, and actually regions that were more exposed to this agricultural productivity shock tend to experience lower manufacturing productivity in a time horizon of around 5 to 10 years after the productivity shock that we're going to talk about in this paper, and the legalization of genetically engineered soy in Brazil. So this is sort of my outline of the main 4 results. Let me now and probably skip this, and I'll go back to this if needed, and sort of start talking about the model first. Give you the main ingredients of the model. I'll spend a little bit of time, background data and identification, and then I'll give you sort of a longer version and a more detailed version of the results I just described. So let me start from the model. Okay, so first of all, what is the objective of this model? The objective of the model is to highlight a mechanism that can explain why a positive agricultural productivity shock, in our case, the adoption of genetically engineered soy, can result in a slowdown in manufacturing productivity growth. The model is an endogenous growth model, open economy with 3 sectors. Let me just describe them in order. So there is agriculture. Agriculture uses land, which we index with T here, as well as skilled labor, which we index with S, and unskilled labor. And we're going to think of GE soy as sort of this skill augmenting technical change that you see here. I'm going to try something very technologically advanced, such as underline something in this slide. So this is what's capture skill augmented technical change in our model. There are 2 manufacturing industries, the H industry and the L industry. Let me start describing the H industry, which is the most interesting one and where the good innovation happens. So the H manufacturing industry also uses high skilled labor and low skilled labor. And it also uses differentiated intermediate inputs. And this KH here captures the number of such intermediate inputs used in the H manufacturing industry. As shown here, an increase in this number of intermediate inputs has 2 effects. First of all, it increases the productivity of the H industry itself. For example, because it generates a more efficient division of labor. I'll make some examples later. But these inputs in the H industry will also sort of have spillover effects in other sectors. And you can already see this by the production function in agriculture, which also has KH. Then there is the L industry. The L manufacturing industry uses 2 types of labor, although with a different intensity, as well as intermediate inputs. However, the intermediate inputs in the L industry are of a different nature. And in particular, they tend not to have all the nice characteristics of the intermediate inputs of the H industry. They do not increase the productivity of the L manufacturing, and they also do not generate positive spillovers on other industries. So let me give you an example sort of to think about this through these 2 types of industry. You can think of the H manufacturing as, for example, the computer industry. You can think of the L manufacturing as food processing. A new input in the H industry could be, for example, a new software that makes management of production more efficient. Now, this software can, for example, improve and make more efficient the division of labor within the H industry, making the H industry more productive, the computer industry more productive. But it's a software that you can use to manage production also in other sectors, and so it has this type of spillovers. Instead, in the example I made before, if the L industry is food processing, these type of spillovers are less likely to happen in this industry. For example, suppose that food processing introduces a new food additive as a new input. That is unlikely to make food processing more productive, and is particularly will hardly generate any productivity spillover in the rest of the economy. This is the assumption I just described. And to complete the picture, there are going to be R&D firms in our model that can decide whether to invest in generating new inputs for the L industry or the H industry. They can decide to invest their time in trying to create a new food additive or a new software for managing production, and the returns that they obtain from generating these new inputs depend on the size of the industry. So when an industry becomes larger, and returns for creating inputs for that industry also go up. So what are the predictions of our model when the economy experiences on skilled labor augmenting technical change? Well, first of all, under a set of assumptions, skilled labor technical change, augmenting technical change will generate a decline in the demand for low-skilled workers in agriculture. And these low-skilled workers will tend to move towards and be absorbed by the L manufacturing industry and the food processing in our example. Now, this reinforces the comparative advantage of the L manufacturing in the local economy, which tends to specialize in that industry. As this L industry expands, the market for intermediate inputs for the L industry also expands. The return for creating new inputs for the L industry increases, and so sort of innovation starts targeting this L industry. And since this L industry, generating innovation in that industry doesn't generate the same spillovers to the rest of the economy, overall productivity slows down. So this is sort of the key intuition of the mechanism, and really it's hard to make it justice in one slide, but this is sort of hopefully the main intuition I went through. Let me now sort of clear all my beautiful drawings here from this slide so that I can actually move to the next. So we bring this idea to the data, and as I said before, the background, the agricultural productivity shock that we're going to use empirically is the legalization of genetically engineered soy in Brazil, which happened in 2003. This new technology is a technology that makes soy plants resistant to a powerful herbicide, which is glyphosate. And you can think of it as a technology that allows farmers to save on several labor-intensive activities, mostly related to weed control. These activities are traditionally performed by low-skilled workers, so when you adopt this technology, you just need less of those type of workers. A couple of graphs to give you a sense of what are the macro trends in Brazilian agriculture in this period, in soy production in this period in Brazil. The left graph shows you this area farmed with soy, and what you see is that there was a fast expansion in area planted with soy in the early 2000s, where area planted with soy basically doubled in Brazil in the span of a few years. And on the right-hand side, you see employment in soy by skill. And we're going to consider skilled labor here as workers that have at least completed 8th grade, we can be more demanding here. It doesn't change the result. But what you see here in general is sort of a secular trend of decline in employment in soy, which actually becomes steeper when soy area expands, which is sort of consistent with this expansion being at least partly driven by the adoption of this new technology, which requires less labor. In general, you shouldn't think about the decline in labor within soy to be the only force that actually sort of pushes workers out of agriculture. Soy in general is very low labor intensive relative to other agricultural activities. So whenever soy in Brazil sort of colonizes a field previously farmed with another crop, it tends to sort of generate a push of unskilled workers out of agriculture. In terms of identification, to identify the effects of technological change in soy production, we exploit variation in the potential increase in soy yield across regions of Brazil. And for this, we're going to use FAO-GUIDE's data, which many on potential obtainable yields that many of you are familiar with. This data, as you know, provides an estimate of the theoretical yield that you could obtain if you were to farm a given crop in a given area under a given set of inputs. And the two maps you see here are the potential yield that you were to obtain in Brazil, different areas of Brazil, if you were to farm areas under high inputs. Our high inputs are computed assuming the use of improved seed varieties, optimum allocation of pesticides and herbicide. And what you see on the central map here is potential yields under low inputs. And that's the inputs computed assuming traditional seeds, no chemicals or mechanization. And we use this data to build a measure of increase in soy technical change for each microregion of Brazil. This is very similar to previous work that we have with Paula, and we define this technical change as the difference in potential yields between the high and the low technologies that you see here. You see there's a lot of geographical clustering in this measure. So in all our empirical specifications, we will control for macro regions fixed effects. So we are really leaving out of variation within the south of Brazil, within the center west, within the Amazon area, within the northeast, within the coastal areas. In terms of data, we're going to use data on so first of all, what's the unit of observation? The unit of observation is this micro region. So there are around 600 microregions in Brazil. Each of them has around 300,000 people. And you want to think of a microregion as always encompassing at least a urban center. Okay, so there's some rural area, there are some rural microregions, but even those rural microregions tend to have a urban center. So it's sort of a good proxy of the relevant labor market for every individual in Brazil. In terms of employment, we're going to use data from the population census. This is from the last two waves, 2000 and 2010. Population census has the advantage of covering formal and informal workers. And then we're going to use social security data, which instead only covers formal workers, but it's actually quite useful when you try to understand the dynamics of what happens within manufacturing, where the informality is less of an issue. For innovation, we're going to use a survey that tries to capture innovation activities of Brazilian firms. And these we will end up using just to classify industries between low and high R&D industries, sort of in the spirit of what I showed you before. Now, why don't we use this as an outcome? Just this survey doesn't provide for sort of geographically measures of innovation that are representative at the geographical level we are studying. Instead, we're going to develop a new measure of innovation based on social security data, and I will describe this measure in a second. Finally, for productivity, we're going to use the yearly survey of Brazilian manufacturing firm. This is a standard manufacturing survey that covers every firm above a certain threshold. That makes it representative at the level of aggregation in this paper. So let me go now through the results. So there are four main results. So let me start with reallocation of labor. So this is what you see here is sort of reallocation of unskilled labor across sectors. So the outcome variable in this regression is going to be the change in unskilled labor between 2000 and 2010, because this is census data, in each sector, in agriculture, manufacturing, and services. And the plotted coefficients capture the effect of a standard deviation in soy technical change. So it basically tells you that micro-regions experiencing a standard deviation larger agricultural productivity shock. In soy, experienced a 2.5 percentage point larger decline in the share of unskilled labor in agriculture, and a 2.2 percentage point increase in the share of unskilled workers in manufacturing. And these are quite large magnitudes if you compare them with the initial shares. This is around 7% of the initial share in agriculture, and this is 16% of the initial share of unskilled labor in manufacturing. There's no differential effect in total employment, so you can really think of these as sort of unskilled workers moving from one sector to another. You see this result is also visible if you look at the social security data for manufacturing. Now, the advantage of social security data is that it allows us to trace the impact of this agricultural productivity shock by year. And this is through the specification that you see up here. And here we are looking at just at formal labor in manufacturing. On the left graph, the outcome is the log of unskilled labor in manufacturing. On the right-hand side is the log of skilled labor in manufacturing. And the figure shows that micro-regions more exposed to the soil technical change experience a faster increase in low-skilled labor, but no differential increase in skilled labor. And these effects, sort of the timing of these effects is broadly consistent with the legalization of GSOI in Brazil, which happened in 2003. There are some effects already in 2002. This is something that we've discussed in the paper, also in previous work. There was smuggling of these seeds already from before. And if you look at the macro series I showed you before, the soy area really start to pick up in 2002. But what more interesting, which manufacturing sectors actually end up absorbing this inflow of low-skilled workers? So what we do here, we split manufacturing into two broad industry, high and low R&D intensive. And this split is based on the median of research and development expenses over sales in 2000. We weight a number of workers. We weight these two sets of firms by, so these two groups by number of workers. So we have the similar number assigned to the below and the above the median. Above the median includes manufacturing of engines, vehicle parts, manufacturing of equipment, pharmaceutical products. Below the median are the sectors I described before. And this is the result I was showing before. Most of this reallocation happens in manufacturing, low R&D manufacturing.
Jacopo, you have about 5 minutes.
Yeah. Sorry, Kostas, I saw you. I didn't say anything, but I saw your. Perfect. So just to let me get to now the result on innovation. Remember that just to give you a recap of the mechanism in the model. In our model, an increase in unskilled labor supply reinforces the comparative advantage in the L industry, and this increases the returns to introduce innovation in the L industry. Now, so how do we measure innovation? That's sort of a challenge because it's hard to measure manufacturing innovation at such a detailed level. So we propose a new methodology. What we do, we digitize the occupational dictionary from the Brazilian Ministry of Labor. This is a description of the task of each of the 2,571 occupations that are reported in this dictionary. We identify a set of keywords that identify innovative occupations. These keywords could be, well, some examples are here, others are in the paper. Happy to discuss more about this. These keywords allow us to identify around 251 occupations that we describe as innovation intense. And these are, occupations whose description includes things like improve process, improve the products, optimize method, generate prototypes, innovate, etc. So this measure of investment in innovation is representative at any level of spatial aggregation. That's a big advantage. We think it also has some advantages relative to patent data, for example. The main advantage being that many firms in Brazil, as well as in other countries, actually do innovate products and processes, but actually don't patent those innovations. And this is especially true for small, medium-sized firms for which the legal cost of patenting is quite high, and they also don't want to disclose that type of innovation to information to other competitors. So this is just an example of what the raw data looks like. Let me skip this. This is just what the task description looks like, and then we find keywords. This measure of innovation correlates pretty strongly with other standard measures of innovation at the industry level. And this is sort of a spatial distribution of the share of workers in innovative activities across Brazil. You see it's, it ranges between 0 and 20% across regions. It's clearly clustered and concentrated mostly in richer coastal areas, but there are actually a lot of like industrial clusters, even in remote sort of rural areas. Sort of all these like darker spots here in the north of Brazil, for example, these are like Manaus, Amirim, and these are sort of, you know, relatively large industrial clusters of, you know, paper industry, chemicals, etc. So let me show you sort of the main result before my time is up. So this is the effect of agricultural productivity shock on innovative activities. And I just want you to focus on the result on the right that shows you that in correspondence, you know, the timing sort of in correspondence with this legalization of GSO in Brazil, there is a relative decline in innovation expenditure in regions that were more exposed to it. And this relative decline is strong and significant in the high R&D industries, the H industries in the model I described before. These effects is quite large actually, and what you see in this, but let me, since I'm almost out of time, let me actually give you one more result, which is the following: that these regions that were experiencing, they were more exposed to agricultural productivity shock and were experiencing this decline in innovation in high R&D manufacturing, are also regions that experience a relative decline in manufacturing productivity in the medium run. This decline in manufacturing productivity happens with some delay relative to the decline in the innovation effort. That makes sense, given that our measure captures input in innovation, while manufacturing productivity clearly depends on the output of innovation. And finally, sort of one concern with this could be, well, maybe you're reallocating workers to low R&D industries. Maybe those are less productive, and so these results is just a compositional effect. While our model would predict that, you know, all industries should experience a decline in manufacturing productivity, and that is what we find when we look at the effect of agricultural productivity shock on manufacturing productivity. We see that those effects are negative both for the low R&D and the high R&D manufacturing. And I believe, Kostas, I'm basically out of time.
That's great, Jacopo, and the paper.
So yeah, thanks a lot. So this is just my conclusion slide, which I will not discuss at this point. Thanks a lot.
Eric, you had the related point on innovation and measurement. Eric,
well, yeah, it was just thanks. Yeah, it was just a measurement point, which is that the measure of innovation, which is very interesting. I think I like it, but it sounds a little bit like it's proxying for skill intensity. No, and so I guess I wonder if I put in a traditional measure of skill intensity and your innovation measure in the same regression, are they going to show? Am I going to show up? Is it actually going to be on the skill intensity, or is it going to be on these particular occupations?
Right. So I think they're definitely correlated. We do that exercise at the industry level, and this is the graph you see here. So Eric, on the right. So at least at the industry level, it seems there are quite a few industries that have relatively high share of skilled workers, but those skilled workers don't seem to be employed in innovation-intensive occupations. So we think this captures something different. There are a lot of high-skilled managers that are actually working in industries that don't produce a lot of innovation, and that I think this is what this captures. But to be honest, we haven't tried to use I think the share of skilled labor as an alternative measure of this, which would also be, of course, a representative at local level, because that data is available at the local level.
Right, but just then I wonder. Yeah. But then is your effect on you're raising the skill intensity? So I think. Or is it, or sort of reducing the skill intensity when you have this influx of low skilled workers, or is it directly an innovation response, right? So if it's just a proxy for skill intensity, then it's interesting, but it's sort of less remarkable than if it's actual an innovation response.
Well, it must be correlated, given that high skilled workers in our data are those that are more likely to be employed in these innovation intensive occupations. This is a measure of innovation input. So these are people whose tasks include coming up with new ideas to solve small problems of businesses. But I'm not sure if this is like perfectly answering your question, but we can stick around and talk about this. I'm happy to remain here online and talk about it.
Yeah, we have many good questions, but I think we have to maybe one more by Joe. I don't know if Joe's had a couple of comments. I don't know if they were answered, Joe Kabowski. Do you want to unmute?
It's about the, I mean, this relates to Eric's, but just how much of this can we just understand as being a demonstration of the Rybczynski theorem? Like what goes against Rybczynski? If we just think that agriculture released, all of a sudden there's an increase in the supply of skilled labor to the manufacturing sector. Is there anything that's against the Rybczynski theorem? Or?
I don't think so. This is actually a Rybczynski force, right? I mean,
It is, okay.
that is actually the way we interpret it also in the paper. Yeah.
Okay.
Okay. Well, that was fast. Maybe the next line was from Paco. Paco, do you want to state your question?
Hello?
Yes, I can hear you.
I can hear you. Yeah.
Yeah, no, just, what's the question? The measure of productivity is our revenue productivity. Is correct?
That is correct, yeah.
And I think that the model is speaking more to a physical productivity effect. So in principle, I guess these results could be interpreted as the distortions on manufacturing firms in areas affected went down. And there was no impact on physical productivity. There could be an impact on physical productivity, but the measure of productivity you're describing doesn't necessarily speak to that. That's the only.
I take your point. Yeah, so we don't have what you want in that sense. So we're going to work with value, revenue-based measures of productivity. This is the most basic one you can think of, actually. It's just value added over the wage bill. So value added per efficiency unit, if you will. But I take your point. Yes.
I really like the paper, though.
Yeah.
Okay, maybe we'll close with one last question by Marina Goma. Marina, do you want to put down your question, unmute and?
Yeah, thank you. I think I got the answer. I was just wondering how much of the increase in the unskilled labor in manufacturing are switchers. So I wonder if some of them were just previously unemployed. That was my question. Thanks.
Right. That's a great point. And as I said before, there is no differential change in actually the number of workers in the following this shock. So what we think we're capturing here is mostly reallocation of workers across sectors rather than a differential rate of entry into regions that experience this shock to a different extent. But yeah, so that is something we have looked into.